All right, what you have in front of you, ladies and gentlemen, is it's what we're going to take our notes on today, okay? Because we're going to be writing nuclear decay equations. Now, if you remember yesterday when we went through these nuclear decay equations, our learning target was to compare and contrast the different types of radioactive decay. So yesterday, what I wanted you to do, I wanted you to be able to identify the different types of nuclear decay reactions. So let's just review. Aiden, what was one type? Alpha decay. Stephen? Positron emission. Amelia wasn't here. Did you watch the video? Do you know another type? Okay. Well, we'll just skip you since you weren't here. Electron capture. We got one more. Kenzie, you got it? Or Kaylin, you got it? Didn't you say positron emission? Okay, there's one more. Beta decay. Good. So those are the four different types of nuclear decay reactions. And yesterday, like I said, what I wanted you to do is to be able to identify them. So if we're thinking alpha decay, we're looking for that helium, okay? If we're thinking electron capture, the electron's going to be on the reactant side. So certain things that we were looking for in order to identify those. Well, today we're going to go a step further. Today what we are going to do is we are going to write nuclear decay equations. So on this sheet, I have given you the four different types of nuclear decay reactions. We're going to go through, we're going to work these, and then I'm going to turn you loose, and you have a worksheet to do on this. So if we remember, okay, X is the symbol for the element, Z is the atomic number, A is the mass number, which is the number of nucleons, which is the number of protons plus the number of neutrons. So this A and Z are going to be very important when we write our nuclear decay reactions. We're going to start off with the alpha decay of uranium-238. Okay? This is the most common isotope of uranium. Remember, I told you that you need to memorize these generalized equations. So this is the one for alpha decay. I definitely know alpha decay is going on because there is that He. There's the helium. There's the alpha particle. Now, when I go through and I write my equation for uranium-238, I need to come up, and I know that the symbol for uranium is U. I know that the mass number is 238. I'm going to slip over to my periodic table. My atomic number for uranium is 92. Now I've got all the information that I need to have to construct my alpha decay because I know that A minus 4, okay, 238 minus 4 is 234. Z minus 2, 92 minus 2 is 90. What is element number 90? It is thorium. And then I simply add on to that my my alpha particle. And ladies and gentlemen, I have done the equation for the alpha decay of uranium-238. Now, one very tough if you know the equation. Now, what I want to do here, and you're going to see with these, I want to give you a little bit of where this happens, okay? How is it used? This nuclear decay that we're talking about, what's some real live things? All right, so I look at this, the uses of alpha decay. All right? Cancer treatments. Okay? The alpha particle destroys cancer cells but lack the penetrating ability to damage the surrounding healthy cells. So they use alpha decay in a form of treatment for cancer. Also, smoke detectors. Okay? The alpha particle from Americanium-241 bombard air molecules, knocking electrons free. These electrons then create an electrical current. Smoke disrupts that current and sets off an alarm. Therefore, you can wake up in the middle of the night if that smoke alarm is triggered. Okay? Something else, spacecraft power. Now, I don't know how much this is used today, but they're talking about Pioneer 10 and 11, Voyager 1 and 2. They're using devices like this as batteries with the benefit of a long lifespan. So in this particular case, plutonium-238 serves as the fuel source, producing the alpha radiation, resulting in heat, which is converted into electricity. Okay, the final one, Coast Guard buoys. Okay, Coast Guard buoys, they're out in the ocean. The U.S. Coast Guard uses alpha radiation to power some of their oceanic buoys. Okay, so it gives them power for a long lifespan. They might not need to go out and replace the batteries as often using this alpha decay. Beta decay is our second one. The beta decay of cobalt-60, which is used in radiation therapy. Well, let's take a peek here. I'm looking at my equation that I need to memorize. So I'm looking right here and I say, okay, what is changing? Okay, A is not changing. Z is increasing by 1. So that tells me that I have a neutron that is changing into a proton. A neutron that is changing into a proton in this beta decay. So I come up and I'm using cobalt. I know that the symbol for cobalt is CO. I know that I have cobalt-60 as my mass number. Cobalt's atomic number is 27. So I know I'm pretty good at math. The A stays the same. A stays at 60. Z is plus 1. So 27 goes to 28. What is element number 28, ladies and gentlemen? That is nickel. And I also have this beta particle given off. Okay, now what I want you to be aware of too, this beta particle given off here, I've also seen this written as just an electron given off. So make sure you're aware of that you could use the beta particle or you could use the symbol for an electron there. I believe that the gizmo that you will do on this uses the electron symbol, not the beta symbol. Okay? So that's just something to make a mental note of, to put that in your memory. Now, beta decay. What's some uses of beta decay? Well, okay, RNT, radionucleotide therapy. Well, what is that? What is RNT? Once again, it's a cancer treatment. Okay? It utilizes beta decay. Okay? Lutetium-177 or yttrium-90 is attached to the molecules ingested where it travels to the cancer cells. Okay? As the radioactive atoms decay, they release beta particles and kill the nearby cancer cells. Carbon dating. Have you ever heard of carbon dating? We're going to do a project on carbon dating coming up. Carbon dating is used to date artifacts, wood, animal remains by checking the ratio of carbon-14 to carbon-12. Okay? What happens is when a plant or animal dies, the carbon-14 that it had in its body starts to turn to nitrogen-14 via beta decay. Using the ratio of carbon-14 to carbon-12, we can approximate the date in which that animal or plant started that specific decay, so it could tell us when that they died. Okay? Electron capture by lead-205 used in insecticides and hair dyes. That's kind of a diverse grouping there. We spray it to kill an insect, and then some people put it in their hair to make it a different color. All right? Kind of different. When we're looking at the electron capture, notice that the electron here is on the reactant side of the arrow. Okay? So the electron is coming into play here. What happens? I look at this Z minus 1, and I can see that my atomic number is going, my atomic number is going down by 1. So that means that a proton is being converted to a neutron. Lead is Pb. So I have Pb. I'm dealing with lead, 205. I look at lead's atomic number, and it is 82. I capture this electron, and it's still going to give me 205 because A does not change. Z is 82 minus 1. Seems to me like that's 81. Element number 81 is thallium. Thallium's not TH. Thallium is T, and I'm going to put that lowercase l, like a cursive L, because sometimes I have trouble with lowercase l's and capital I's. Now, one thing that you might see with this also, with this particular one, you might see something like this. Have another plus, and then see something like this. That right there is a gamma ray. So, also given off could be gamma rays. Now, I'm not so concerned that you know. I'm more concerned that you know this equation right here, okay? But you just need to know, recognize, I say, not know, recognize if you see that this particular right here, if you see that, you know what it is. It's a gamma ray. All right? Now, electron capture was a little tougher to find some uses on it. So, uses of electron capture detectors. What these detectors are is they're used in environmental testing for detecting pesticides, herbicides, and various halogenated hydrocarbons. Now, what that means is it's just a hydrocarbon that has a halogen onto it. One of the common ones that when I was looking into this stuff was Freon. Okay, anybody ever heard of Freon? Okay, Freon is a refrigerant. It used to be used, and I'm not sure whether it still is, but like refrigerators to keep things cool would have Freon. Your air conditioners in your cars would have Freon. Your air conditioners in your house would have Freon. Now, I don't know if they still use Freon or not. I would have to look into that, but that's what this halogenated hydrocarbon is. Now, what's the idea with the electron capture detectors? What's the big deal about them? Well, they are 1,000 times more sensitive than the flame ionization detectors. So they're a lot more sensitive than the previous detectors that they were using to find these things. They're able to measure components at parts per billion and parts per trillion levels. Okay, what does that mean? We'll study parts per billion. parts per trillion later on in the year, but you might see something like 1 part per billion. That means if there's a billion little spheres, one of those spheres would be the 1 part. So it could find 1 part per billion, which means it's pretty sensitive, okay? Pretty sensitive to detect that small, okay? I wouldn't want to be going through a billion golf balls trying to find the red one. I mean, think about it. Could be tough. Positron emission by oxygen-15. It is used as a tracer in the movement of regional blood volume and flow. So we're dealing with oxygen-15 here. So I know that my equation tells me that I have this positron here that's being given off. I can see that Z is -1. So I have a proton that is being converted to a neutron. So I have oxygen, 15. I know oxygen's atomic number is 8. It's going to give me 15, 7. Element number 7 is nitrogen. And I also have this positron given off. So I have the positron there that is given off. And remember that the positron is the positive version of that electron. Now, have you ever heard of positron emission tomography? No? Yeah? Yeah. That is a PET scan. Now, what's a PET scan? Carly? Have you had one?
No, we just talked about psychology.
Okay. This PET scan, I'm going to show you some of them, though. Here's the machine that is used for a PET scan. Now, that doesn't look too much different than the machine that I had my MRI on. Has anybody had an MRI? Did the machines look something like that? Okay. And they were really, really, really noisy machines. Okay. So this is the machine for the PET scan. Now, the PET scan is an image test that helps reveal how your tissues and organs are functioning. A PET scan uses a radioactive drug that we call a tracer to show this activity. The scan can sometimes detect diseases before it shows up on other imaging tests. So this radioactive tracer shows up on the PET scan. And when they can see that tracer, they can sometimes detect the disease. Now I'm going to show you some things here on this slide right here. Excuse me. The far left one here is a CT or a CAT scan. Okay? You can see that this is, right here is the neck, okay, coming down here. On each side are the lungs. We can see the pelvis down here. It's a pretty good image. Here is the PET scan, okay? It's a little bit darker. It's not as good as an image, but see that little spot right there? That's the tracer right there where I've got my arrow at, okay? So when we put these two together, this CAT and this PET scan, you can see the different body parts better, but see then right here is that tracer. What that is right there is that bright spot on the chest is lung cancer. Okay? So if you look all the way over here in the CAT scan, does the CAT scan show anything with that? Absolutely not. It does not. But when we have the PET scan, we can see the little tracers right there. And if we put them all together, but the CAT scan and the PET scan, we can see exactly where in the part of the lung that tumor is. Okay? So just some common or some uses for these different types of radio or of nuclear decay.